Let me go ahead and start the recording. I'm going to use this paper again, the one I gave you last time. Do y'all keep that? So it had the two axes on it. We drew on one of them. We're going to draw on the other one today. I have an extra. Extras. Hey, I run out of the ones I already graphic. Plotting the axe. I draw on that box. Last time. Um, don't let me forget to pass out the roll sheet. Um, so they're the homeworks, right? I think these were already posted. I added another one here. Hopefully, we'll at least introduce the idea of cross products today. We're going to talk a lot about dot products, but those are pretty easy, except, well, their applications are not always easy, but computing a dot product itself is easy. It's a little bit trickier to compute a cross product. It just is a little bit more involved, but it's not difficult. Neither one of these operations is painstaking. And then talk also, maybe not today, but next time, about applications of cross products, what these operations are good for. But you do have a homework that's due tonight, right? This one on space coordinates, right? So I think that's the first homework on three-dimensional space. Due this evening, and I thought that you may have questions on the last two problems. Am I right about that? Were those the hardest ones? Yeah, those involve force vectors. We're going to look at those and see if we can at least start them. But this is not due till midnight, right? Okay, so you still have the midnight to finish this one. I was going to point out, where did I put it though? See, maybe it's over here and I can't see it. Yeah, there it is. I was going to point out that I did post the sample test for the first test, which is supposed to be next a week from Wednesday, but so not this Wednesday, but the coming Wednesday. But I don't think we're not going to hit that target, so we'll have to postpone that somewhat. But I'm not sure when. So I didn't announce that on the website that this was available, but it is available now, so you can start looking at it. So this is the sample test for test number one, but given the amount of material that I included on the sample test, to get through that, it's going to take us longer than than next Wednesday to get comfortable with that. So we'll have to postpone the test a little bit. So, but anyway, so I'm not sure exactly when yet. Maybe we'll know better today or Wednesday exactly where we're going to be. But anyway, it is there. So if you want to look at it, it's there. You could start on it, on the first problems, for sure. Be sure you read the disclaimer, which just says, this sample test is not the test, right? Okay. So, in particular, it's important to keep in mind that the sample test is, does it say it there? The sample test is longer than the test. Okay. All right, maybe I didn't put it there. Is it on there? Yeah. So when you open that, don't freak out and say, oh my God, we're not going to be able to finish this in a short period of time. No, this is just a sample test. So I included lots of stuff on there just to give you plenty of practice, but the test will fit into the time period, right? So again, this is practice, right? So the problems are very similar to the homework problems, except of course they're going to be with pencil and paper to feel more like the test is going to feel, right? Okay, unlike doing things on homework and having to type in answers, not being able to show your work, and then immediately getting feedback whether your answer is right or wrong, right? Okay, because obviously none of those things happen on the test, so they won't happen on the sample test either. Okay, so it's there, and eventually I'll post an announcement in WebAssign that it's there. when we officially set the date of the first test. Okay. All right. So I said all of the stuff that I needed to say. Let's look now at let's look at this homework and see if we can make sense of the last two problems. The next to the last one is not that bad, but the last one is just a little bit involved. Although it's just an extension of number 12. Okay. All right. So this one, not so bad though. So you have this wire, right, that's supporting this tower. Okay, so that the tower won't fall over. And the force on the wire is 510 pounds, right? There's some force on that. There's some tension on that wire, right? Um, and it says, just using the illustration here, we want to write in component form. Oh, in component, okay, not in standard, but we want to write in component form vector that represents the tension on the wire, right? Because we're going to use that idea in the following problem. So we have to be able to do this first, right, before we can solve the next problem, right? So again, we're going to write a vector that again represents the force that's on this wire. So the direction of the vector is pretty obvious, right? Because it's going to correspond exactly to this wire, which appears to be taut there, right? Okay, so fortunately, we don't have any sag here, right? So we just have this nice straight line, right, from the top of the tower down to this where it's staked in the ground there, right? And they've drawn nicely for us. They've superimposed a set of axes here nicely on the picture, right? So we can figure out the coordinates of this vector easily, right? However, remember, we've got to make the only tricky part here is making sure that the magnitude of the vector you write down matches the force in the problem. Okay, so you cannot just write a vector that represents that wire, because you're not going to end up with more than likely, I mean, I guess you could by happenstance, but more than likely you're not going to end up with a vector whose magnitude matches the force that has to be on the wire, right? So you have to adjust that vector somewhat, okay, that you write down here. See, we want a vector that represents the force. It's not a vector that corresponds exactly to this geometric picture that you see here. It's a vector that represents the force on the wire, right? Sort of not the picture of this, wire, although the picture of the wire is important to us, okay? All right, so let's see if we can do that. Now, the only kind of question here, and maybe it's not important, but anyway, this is the way the book answers the question. We're obviously going to write a vector that corresponds to this wire, correct? But the question is, vectors have direction, right? So we're not going to write down a line segment there that corresponds to that wire. We could do that, right? But we need a vector, so that has direction. So the question is, which way is the direction going? All right, and so the debate here, is how is this force directed? The book is going to assume that the force is directed toward the ground. Okay, so if you answered that, if you were writing the vector so that the force is directed up, which is reasonable to do, okay, you're going to get signs wrong, I think. Okay, so that's really kind of an annoying issue here. All right, but so I'm sort of telling you what the answer is there. All right, so assuming that the force is moving in this direction, right? Is directed from top to bottom, then let's try answering the question, right? So let me lower the screen here and give us some paper to work with. Do y'all see do y'all have the picture in mind there now? We can refer back to it, but if we can remember as much of it as we can, so we don't have to keep flipping tabs, right? Right, this distance is 75 feet, I guess, right? No, this distance is 75 feet, right? Okay. this distance is 50, right? Then the height of the tower is fixed. But notice the way they've got the axes drawn here, right? This is a first coordinate perspective, right? Positive part of the positive part of the x-axis, right? Positive part of the y-axis. Now that I told you to remember that, I'll probably promptly forget it. So y'all will have to remind me here. Let me see if I can find some blank paper, or we can add some blank paper, and we may need to add some here. All right, so let's make our initial stab at that. Let's make our initial stab at writing down that force vector, right? So I'm just going to write a vector there that corresponds to. I'm just going to write a vector there that. Let me not call it F. I'll use that for the force vector. But we're gonna. So let me just make up a vector U here. But we're going to modify U to be the force vector F in just a moment. All right. I just want to let U be the vector that sort of corresponds to the picture of the wire, right? Okay. So so what's the initial point of that vector? That's the top of the tower, because remember I told you we want to think of the vector as going from the top of the tower down to the ground. Okay. All right, so what would that be there? I think on the z-axis, I know, right? Was that 100? And then that was just right above the origin, right? On the xy plane, right? So these are 0 and 0. Okay, all right. So that's easy. And then what about the terminal point there? This must be 0 because it's on the ground, right? And then where was it located there on the xy plane? That's what we were looking at, right? So that was what? 75 on the x-axis, right? And negative 50 on the y-axis, right? So if you write U down in component form, right? Remember, we want to take, what is it? A terminal minus initial, right? So this is in component form. So 75 minus 0 is 75, right? Minus 50 minus 0 is minus 50, right? And then 0 minus 100 is minus 100, right? That third component has to turn out to be negative, okay? So I think in my initial thoughts about the problem, I was writing this down as positive, okay? And which is fine, I think, but it's just on a test that would be okay. But I think WebAssign's going to grade it wrong, so might be annoyed by that. All right, now that is not the force vector, right? Because we've got to get the magnitude correct, okay? And I don't think the magnitude of that vector matches the force that we want on the wire, which was in our version of the problem, was it 510 pounds? Okay, so we need to adjust this vector. The direction is correct, but we need to adjust this vector so that it has the right magnitude. This is so easy to do. Look, so that's how we're going to get our force vector F. All right. Look, this is easy to do. Take this vector and turn it into a unit vector with same direction. So take this vector, make it a unit vector with the same direction, and then multiply it by the appropriate force. And that will give you a vector with the correct magnitude, right? So here's what I'm suggesting to do. How do you take a vector and transform it into a unit vector, or find a unit vector that's a vector of 1 that has the same direction? Right. Divide by the magnitude, right? You divide everything by the magnitude. So we're going to take U and divide it by its magnitude, see? All right, that will give you a vector in the same direction as U. So from the top of that tower down to that where the stake in the ground is, but the length will only be 1. All right, the magnitude will only be 1. So we fix the magnitude easily here because this is a unit vector. We can fix the magnitude easily just by multiplying by the magnitude that we want, which was what? 510? So see, it's just so easy as to do that. That's all that's required. The rest of this now is just purely computation. You have to figure out what's the magnitude of U. So the magnitude of u there is what? The square root of all of these things squared. So 75 squared plus a minus 50 squared, and then plus the negative 100 squared. Make sure you take the square root of that, right? Okay. And then divide all these components by this quantity, and then multiply through by 510. So I'm not going to go through all that arithmetic for you, all right? And it says we want the answers to what accuracy there? 12 decimal places? No, 3 decimal places, right? Well, that's still a lot, okay? So, of course, we're going to end up with decimal approximations, right? This is certainly not going to be a perfect square, right? So we're not going to be able to simplify the square root. So ultimately, there we'll need to write down some decimal approximations. We want to write them down to 3 decimal places. Okay. You don't have to do the computations for me. We're not going to fill in the answer here and check it, but that's how the problem works, right? Okay. So divide all of these by this quantity, whatever that turns out to be, right? Then multiply through by 510, and there you'll have the right. Then you'll have the right force vector. Okay. Now let's see. Now primed with that knowledge, let's see if we can figure out how to start the next problem. Okay. So it's very similar, right? Except you've got this concrete wall, but also being held up by these, well, in this case, it's ropes, right? But you have tension on the ropes. So a precast concrete wall, right, is temporarily kept in this vertical position by these ropes, right? We want to find the total force exerted on this stake, this pin here in position A, right? Okay, and it tells us, though, the force on these ropes, let's see, the force on this rope from A to B is, what is it, 410 pounds? And the force on this rope from A to C is 640 pounds, okay? And so we want to find the total force that is being exerted on this stake. Now, that's not just the sum of the two forces, I don't think, correct, right? Because of the direction of the ropes, okay? So that's going to affect the total force there that's being exerted on A, all right? So unfortunately, you just cannot add up the 410 and the 640. I think if both of those were if both of these ropes were in the same direction, then you could just add up the force, all right? But a little bit more complicated situation, right? Okay, well, look, the only difficult part here, if there is a difficult part to this, is figuring out how to express the force on these two ropes, right? Which is exactly what we did in the previous problem, except we'll have 2 vectors now instead of just 1 vector, right? So we'll have 2 force vectors. We'll have this force vector, right? The one that corresponds, to this rope from A to B, right? And then, I can't draw it here. Okay. And then we'll also have this force vector, the one that corresponds, to the rope from A to C, correct? However, now the book is going to change on us again, or not again, but they're going to switch on us here. And these forces, they're thinking of as moving in this direction. Okay, so instead of from down to from the top of the wall down, they're thinking of from the stake up. Okay, so they switched on us. All right, so so be careful of that in your solution. All right. All right, so now, of course, what we have to do here is superimpose a coordinate system on this picture, right? We have to superimpose a coordinate system on this picture so that we can write down vectors, right, corresponding to the ropes, correct? So how do you want to do this? Do we want to let the origin be right there? Right there where this dotted line I guess that's the line from A to D, where that is right beneath the wall. We want that to be the origin. So if that's the case, then this point, what would the coordinates of that point be? No, I think that okay. So well, let's go a little bit further. All right. So if we want this to be the origin, I need to talk about which axis is which. Right. So we want this to be the y-axis right here. Okay, like in the previous picture, and this one to be the x-axis. Okay. Well, let's make it match the previous picture. So, so in the previous picture, right, this was this would be the positive side of the x-axis, and this is the positive side of the y-axis. Or we could flip here. We can let this be the negative side of the x-axis, and this be the positive side of the x-axis. I think the y-axis, or we can let this be the x-axis running from left to right. Do y'all have any preference here? I think let's just keep it corresponding to the picture above, right? So here a positive part of the x-axis, here a positive part of the y-axis. So that being the case, then what's this point? Looks like 8 on the x-axis, right? And what's this height here? 6 on the z-axis, right? And then on the y-axis, from left to right. What? What's confusing y'all here? Huh? All right, so for this point, maybe I'm confusing you because I'm going out of order. What's the x coordinate? X coordinate of this point? 8, right? Okay, and the z and the y coordinate of this point? 0, right? And the z coordinate of that point? 6, right? So did we remember that there was 806, something like that? Yeah, okay, 806. All right, and then of course for this point, 0, right? 10, 0. Yeah. Yeah, 0, 10, and then 0 on the z-axis, right? Because we're on the ground, correct? Yeah. So don't forget the z-axis. And this point back here, is this symmetric? So I guess that's halfway, right? It doesn't quite make that clear though, does it? So this is what
It says the length of the
oh, I do see that. Yeah, okay. So this is all right. So it's not symmetric, right? This is 8. So this is 10, correct? All right. So y'all had it right. So minus 10, 0, 6 again. Okay. All right. So let's try writing those. Let's try writing those down. My goodness, before I forget them. All right. So point A there was what was point A? 806. Yeah. Okay. A is the point in front.
Yeah.
Oh, I'm sorry. B. Yeah, you're right. Okay. All right. So B, and then A is, so that was the point on the ground. But I do know this was 0, right? 0, 10, 0. And then finally C, that's the point in the back. Negative 10, 0, 6. Oh. All right. And now finally, let's write down, well, not finally, right, but let's write down kind of our initial stab here at those, kind of our initial stab at those rope vectors, right? So we have from A to B, right? So let's call that one U, but you can also label it like this, right? Okay, vector from A to B. It's kind of clumsy notation. And so we just have to take the difference in the coordinates, right? So make sure I do this right. Is that 8 minus 0 is 8, and then 0 minus 10 is a minus 10, and then 6 minus 0 is 6, right? Okay. And then let's call V there. The other vector which we're interested is the one from A to C, okay? And so minus 10, is it minus 10 again? And 6? All right. Okay, so those are kind of the vectors that geometrically represent the ropes, right? But they're not representing the force because the magnitudes are not correct. So how do we fix the magnitudes? That's right. Convert these to a unit vector, right? So you're going to calculate U over its magnitude, right? To get a unit vector, and then multiply by the force that you want, okay, on that vector, which one was that one? 410 or something like that? Let's see, from A to B, 410. So just multiply that by 410. So that's going to be a little bit messy, right? Okay, but that's the arithmetic you need. And let's call that, well, let's just call that F sub 1. All right, so that's the force vector on that represents that tension on that rope from A to B. And then same trick, right? To fix that force vector from A to C, except the tension there is 640. So this is going to be different in your version of the problem, okay? These forces will be different in your version of the problem, but the locations of the points will be the same. The picture is the same. Now, none of this answers the question though, okay? Because the question is, what's the total force on that stake that's located at point A? But now the question is easy to answer. What do you just have to do? Add the forces together. That's right. Okay. So the total force is going to be the resultant, right, force that you get from adding these two forces together. So let's call that F, and that's just now F1 plus F2, okay? And you don't have to worry about adjusting the magnitude here, right? Because that's what you're trying to compute is what's the magnitude of that? What's the magnitude of this vector? That will tell you the force on that stake, right? Okay, so once you've calculated that vector, then compute its magnitude, right? Okay, and the magnitude is force that being applied to that stake, right? So kind of a multi-step process there, but once you sort of get a feel for how force vectors are set up, it's not that bad. But please remember this trick, right? Okay, so if you want to normalize or unitize a vector, right, just divide it by its magnitude, and then you can find a vector in the same direction with any magnitude you want, right? Just by multiplying in the magnitude that you're interested in, correct? Okay, so that's how you sort of change vectors, right? To keep the direction, but alter a vector to whatever magnitude you're interested in. Sometimes the I don't know if they give you a video for these problems. Do they give a video for these problems? Or do they give any help with these problems? Did y'all try that? Sometimes their solution steps are a little bit more convoluted, I think. Okay, so I think this is the shortest way to get at the answer. What they're doing is the same thing, but they're kind of explaining it, describing it a little bit different. Okay. All right. Well, let's switch back now to the notes. And we had just last time started talking about dot products. So dot products are very easy to calculate. So you won't have difficulty computing them at all. It's the applications of dot products there that are really of interest to us. So if you have two vectors, if they're two-dimensional vectors or three-dimensional vectors, either one, you can calculate what's known as the dot product between those two vectors. And we indicate that by using this symbol, this operator, a little dot. So it looks kind of like multiplication, right? And it does involve multiplication. And the way you compute the dot product of vectors is you simply multiply the corresponding components of each vector and then add those products together, right? So in 2 dimensions, right, if these are your two vectors, to compute the dot product, just multiply the first components together and the second components together, then add those two products. In 3 dimensions, same thing, except you'll have 3 products to compute. You multiply the first components, the second components, and the third components all together, and then just add all those up. So it's actually harder to read the description of the technical description of the dot product than it is to compute a dot product. You only have to do it once there to really get it. I wish I had put this in 3 dimensions, but these are in 2 dimensions. Let me pass out those usual sign in the same slot, right? So let's see. So suppose we've got these vectors and we want to compute u dot v, okay? And sometimes you can drop the dot and you see u and v written side by side and you know they're vectors, then that probably means dot product. Let's see, what is the dot product of u and v here? Well, again, you just multiply corresponding components, right? So you would have 2 times 5 plus a negative 2 times times 8, right? Negative 2 times 8. So that's what, 10 minus 16, which is negative 6. So of course, dot products can be positive or negative or 0. And 0 is going to have, for dot products, going to have special meaning to us, however. And what I was stressing last time at the end of class, so you probably forgot, is when you compute the dot product of 2 vectors, do not get a vector. So the dot product of 2 vectors gives you a number. It gives you a scalar. Okay. So when you don't get a vector dot a vector, it doesn't give you another vector. It gives you a number. So you have to kind of sort of keep that in mind sometimes when you've got expressions involving vectors and you have operations in those expressions. You have to make sure that you're sort of at the order of operations is correct there. So here we're taking u dot v, right? Okay. And then notice I don't have an operation there. So that is would be understood to be multiplication, right? So I have something multiplying times w. But what sort of product is this going to be? Yeah, that will be a scalar product, right? Because the dot product will produce a number here. Since that's in parentheses, we're going to do that operation first, right? Okay. And then that will produce a number. And then we'll take that number, that scalar, and then multiply it times the vector w, right? Okay, let's try doing that. So u dot v, oh, we already calculated that, right? So that's minus 6. So I have minus 6 times w, and so this is just a scalar product, right? So we just have to remember what w looked like, and then just multiply both components by that scalar. What was w? Minus 4 and 3. So we get oops. So we get here, and notice you're going to get a vector here. This will be 24 and what, minus 18? So your ultimate result here is a vector, not a scalar. Here, I'll let y'all try this one. See, so y'all can do this one pretty easily. What sort of thing are we going to get out of this, though? So will we get what? Yeah, yeah. In the end here, you'll have a scalar. Make sure though that you follow the correct order of operations, right? So that means work in parentheses first. Work inside the parentheses first. Oops. Do y'all wait? Let me. Shall I write these so y'all can see them? Sorry about that. Okay, so there they are. All right. So now see if you can. I'll see if you copy this out. Okay, did y'all get that? Is that pretty easy? Let's see, what is 2 times v going to be there? Yeah, first we have to think about how we're going to write that down. Let's write that down in component form. So what's 2 times v going to look like? Just what, 10 and 16? Right? Okay, so that's just a nice scalar product. And then we form this dot product, right? So we just multiply the corresponding components, right? So you're going to have 2 times 10, that's 20, right? And then minus 2 times 16, that's minus 32. So 20 minus 32 is minus 12. So we get a scalar here, right? Minus 12. The next part there, D, just makes an observation for you. Not really all that interesting, but when you take the dot product of a vector with itself, right? Of course, what you're going to be doing is multiplying the components times themselves, right? So in other words, you're squaring the components. So W dot W would be 5, W dot W would be minus 4 times minus 4, better known as minus 4 squared, right? And then 3 times 3, right? Better known as 3 squared. So when you dot a vector with itself, you're just squaring the components, but notice you don't take the square root here, right? You just take the sum of the squares of the components. You do exactly the same thing, right, when you're computing the magnitude, right? So when you're computing the magnitude of the vector, you also take the sum of the squares of the components. But to calculate the magnitude, then what do you additionally do? You take the square root. But of course, you don't do that when you're computing the dot product. So what that means, of course, is that the dot product is going to be the same as the magnitude of the vector squared. So so these two quantities are really just identical. Let's see, what's that? 16 plus 9, 25. Okay. And of course, magnitude squared here also turns to 25 as well. Now, what are dot products good for? Oh, all sorts of things, but here's the first thing, okay? It's going to give us a really fast way of computing the angle between two vectors, okay? So, of course, if you have two vectors and you assume they're in component form, right? Okay, then they would both be located so that their initial point is at the origin. So if you've drawn both vectors so that their initial point is at the origin, then you have an angle, right? You can compute an angle between the two vectors, actually two angles here between the two vectors, right? You may have an acute angle and then also an obtuse angle, an angle less than 90 degrees or an angle bigger than 90 degrees, unless the two vectors are parallel to each other, right? If the vectors are parallel to each other, then that means the angle between them would be 0 or 180 degrees, okay? These two vectors, by the way, the angle between them is 180 degrees. Those are also considered, these vectors would also be considered parallel. I drew that angle. I didn't draw that angle very well, right? Let's draw that in counterclockwise fashion like this, okay? All right, so anyway, if you have angles in standard position, right, then they have angles between them. And the dot product allows us to determine what that angle is. So I'm not going to prove this theorem for you. There's a geometric proof to this theorem, but we're not going to go through the geometric proof of the theorem, just the statement of the theorem. It's a very simple theorem, okay? And we're going to use it repeatedly, okay? So this theorem says the cosine of the angle, right, between the two vectors, and this is the acute angle between the two vectors, or not acute, but less than the angle, the smaller angle between the two vectors, okay? The cosine of that is given by this quotient, all right? So it's the dot product of the two vectors divided by, this almost looks like a dot product in the bottom also, but remember, this is not a dot product because this is a magnitude and this is a magnitude. So this is just the product of the two magnitudes, all right? So notice the dot operation means different things, slightly different things in the top than it does in the bottom. This is the dot product of vectors. This is the product of two scalar values, okay? But the dot product is also a scalar value. So ultimately here, you just get a scalar, you just get a number, right? Which of course the cosine of an angle is going to be a number. So for this equation to make sense, the right-hand side here has to be a number, which it is. Okay. If you slightly transform the equation by multiplying both sides by the product of the magnitudes, the denominator here on the right-hand side, you get just this alternative form of the same equation, which says the dot product is the product of the magnitudes times the cosine of the angle between the two vectors, the smaller angle between the two vectors, okay? All right. So we're going to use this repeatedly. We are ultimately going to stumble across another formula similar to this one that gives us the sine of the angle between the two vectors, okay? But it doesn't involve dot product, all right? So first here, just cosine, but cosine is pretty good, right? All right, so let's see what this example tells us here. In the diagram above, I claim these are the two vectors. So this vector u in standard form is supposed to be 3.64i plus 2j. Who knows if that's true or not, okay? 3.64i plus 2j. Well, it looks reasonable, okay? And the vector v here over there in the second quadrant, that's supposed to have in standard form minus 3i plus 5.196j. Minus 3i does look like it could be minus 3i, and then 5.96. Well, I guess it could be, right? J. 5.196J. All right. We just want to estimate then that angle theta between those two vectors. Okay. So this is just trigonometry, correct? And of course you'll need a calculator there, right? So according to our formula, let's see if we can remember that formula already. It's a very the formula has a nice structure to it, so it's easy to remember, right? Cosine of theta is what? It's the dot product, right? Divided by the product of the magnitude. So it's a really easy formula to recall. Now, how easy is it to use? I don't know, because you've got to compute some magnitudes, right? So it is a little bit messy here. Let's see, what is U dot V? Oh boy. Okay, so can we do that here? U dot V is this times this, right? So 3.464 times a minus 3, and then plus 2 times the 5.196. So you have to do those calculations. Let's see, this is going to be negative 10 something. What does that work out to be? Can y'all do that for me? 452 or something like that. Negative 10.392. What now? Okay. Is this the same? Oh, weird. So what happened here? Did I write something down fishy or? No. Okay. All right. All right. We don't have to be suspicious of ourselves, right? Just because we got 0. It does make though the denominator superfluous, right? So here you don't have to compute the magnitudes. So we're lucky here. We don't have to compute the magnitudes, right? Because what is this fraction going to turn out to be? What? Huh? No, 0, right? Okay. It's going to turn out to be 0, correct? Because 0 is in the numerator, right? It's when you're dividing by 0 that it's undefined. Okay. I don't think we're dividing by 0 because I'm pretty sure these magnitudes are not 0, right? Okay. But we can see those vectors have them. All right. So we just get the cosine of theta is 0, which means theta, is what? So what's theta? That's the arc cosine of 0. And what's the arc cosine of 0 there? Pi over 2. Sure, right. Okay. So it was just an easy problem for us. All right. So we get theta is pi over 2. Oh, cool. All right. So that means those two vectors are, if the angle between them is pi over 2, then how do you describe those two vectors? Orthogonal or perpendicular. Okay. So those vectors are perpendicular to one another, right? They meet at a 90-degree angle. Okay. Oh, well, now that's important, right? Okay. So how do we know? How can we test to see if two vectors are orthogonal? if their dot product is 0, right? If their dot product is 0, because in that case, right? In that case, you're going to end up with this ratio being 0, right? Okay, meaning that the angle between them is 90 degrees, okay, or pi over 2. Oh, all right, so that's already helpful, right? So we can test to see if two vectors are perpendicular or orthogonal by just computing their dot product. If their dot product is 0, we know they're perpendicular, okay? Now we're going to be working that's going to be really useful to us because we're going to be thinking about a lot of perpendicular vectors, right? So perpendicular vectors are really going to be important to us in the course. They're really helpful. All right. Well, let's try some here. Let's try at least. Well, I have a better idea. Well, no, I better let's do one. Okay, so here's a 3D version. Okay, but the formula works just fine for three-dimensional vectors as well. Okay, so let's see if we can find the angle between these two vectors, which we have drawn here. Does that look like those two? I have no idea. Okay, but there are the two vectors v. One of them is -4, 0, and 2. Well, that is 0 on the y-axis by default there, because notice our y-axis only goes up to, looks like our y-axis only goes up to 0, right? And 0 on the z-axis, is that 0 on the z-axis? No, on the x-axis, right? So 0 on the x-axis right there. Okay, 0 on the y-axis. I'm sorry, -4 on the x-axis. So apparently -4 on the x-axis is over here somewhere. And then 2 on the z-axis. Yeah, this is just the way they've got this box drawn. Okay, that vector's in the corner of this this box. And here apparently is the vector u, 3, -1, and 2. So it certainly looks like they well, they're certainly not parallel to each other, right? Okay, in this picture, maybe they're perpendicular, though. I'm not sure. Okay, so it's very hard to tell from this. Very hard to tell from this picture. All right. Well, let's try. Let's just see what happens, right? So cosine of theta is going to be again, right? It's u dot v over the magnitude of u times the magnitude of v. Let's see. Does this work out to be 0? Doesn't look like it, does it? So the dot product there is -12, and then plus a 0, and then plus a 4. Okay, is that right? Did I do that right? So that's -8, which is not 0. So great, we're not going to have perpendicular vectors here. That would be a little bit boring. So not perpendicular vectors. So now we do have to do the dirty work of computing their magnitudes, right? What is the magnitude of u there? Let's see, square root of 3 squared is 9, right? -1 squared is 1, and 2 squared is 4. So we have square root of 14. And then magnitude of v there is, what is that? Square root of -4 squared is 16, plus a 0, plus a 4. 2 squared is 4. So we have square root of 20. So I get square root of 14 times the square root of 20. If you want to, of course, you can simplify. You can use your calculator to estimate square root of 14 and square root of 20 separately if you want and multiply them together. Or you can also write this as the square root of 14 times 20. What's 14 times 20? Is that 280? So you can also just compute square root of 280 to get a decimal approximation for this. So it's -8 over square root of 280. Can y'all give me that approximately? Notice that's negative, so that's going to be a negative quantity. So what does that already tell you about the angle? The angle between them. Is it in the first quadrant? Is that angle between 0 and 45 degrees? No, because cosine is positive in the first quadrant, right? So that means the angle is already in the second quadrant. So it's a little bit bigger than, I'm sorry, a little bit bigger than 90 degrees. I'm sorry, a little bit bigger than 90. I said 45, but right. It's in the second quadrant already. Okay. So slightly, at least slightly bigger than 90 degrees. What is this approximately? -8 over square root of 280. Minus 0.4781. Okay. And now just take the arc cosine of that. Okay. With your calculator, right? So arc cosine or cosine inverse of minus 0.4781. And we get about, what does that turn out to be? 118.56. Yay. Okay. So indeed, a little bit bigger is bigger than I thought it was actually. So it's not quite up to 135 degrees, but it's well past 90 degrees. Okay. That angle between those two. These look like they're perpendicular, right? Okay, U and W look like they're perpendicular in that picture. So we can test that easily just by doing what? Yeah, so just quickly compute the dot product there of U and W and see if it turns out to be what? 0. So just compute that quickly, the dot product of U and W, and see if that turns out to be 0, and then you know that they're perpendicular. Right, so wouldn't have to do any more computations. Did y'all do that? Does it turn out to be 0? Yeah. Okay. Right. So, yeah, U times U dot W, I mean, there is, so sometimes I'll say times, I should say dot product, but when you're saying one vector times another one, well, I should say dot, because we're going to have another product of two vectors that's different than the dot product. So, yeah, so it's 1 times 3, right? And then plus a minus 1 times a minus 1, and then plus 2 times a minus 2, right? So indeed, that all adds up to 0. So so that picture is pretty accurate there. Those vectors are perpendicular, and these vectors appear to be parallel. Okay, B and Z appear to be parallel, except they're just pointing in opposite directions, right? V here is pointing up, and Z there is pointing down. That's a little arrow at the end of that vector Z, which is hard to see. But they still appear to be parallel, even though they're pointing in opposite directions. So let's try computing the angle between them, and we want to end up, of course, with what? Yeah, we want to end up with 180, right? Let's see what happens there if we do end up with 180. So we get here that cosine of that angle is V dot Z over the magnitudes. So let's see, what is that dot product look like? Let's see if I can find V and Z there. Here's V and Z. So V and Z, their dot product is going to be what? -8, -4 times 2, right? And then plus 0 times 0 plus 2 times -2 is -2, right? This is -8. So this is a -2. So that turns out to be -10. Okay. So I'm hoping, remember the other calculation here is, right, is I need the product of the two magnitudes. So I'm hoping that the product of the two magnitudes will turn out to be what? See, I want the angle between them to be pi, 180, right? What's the cosine of 180? -1, right? So I want the dot product divided by the product of the magnitudes turn out to be -1. Well, the numerator is -10, so that's good. So I want the product of these two magnitudes to be what? 10, right? +10. So that I'll end up with a quotient of -1. It's going to be positive because the magnitudes are both positive. So when you multiply them, you'll get a positive quantity. The question is, does it just turn out to be 10? Let's see, what is the magnitude of B there? That's the square root of what now? Is that 20? And this one is square root of something or other. Is it 5? Yeah, okay. And indeed, right, when you multiply those two magnitudes together, square root of 20 over square root of 5, I think you get what you're looking for, right? Remember, this dot product was -10, and this denominator is square root of 20 times square root of 5. That's better known as the square root of 20 times 5, which is 100. And so indeed, we get what we're looking for, right? So the cosine of theta is -1, and that just means theta has to be pi, right? The arc cosine of -1 is pi. Now, if this quotient turns out to be +1, right? That means the angle between the two vectors is what? See, if this is +1, not -1, but if this expression turns out to be +1, then you're taking the arc cosine of +1. What's the arc cosine of +1? 0, right? So that means the vectors are what? Parallel again, right? But in the same direction. Okay, they would be both in exactly the same direction. Because the angle between them is 0, right? Okay, so they have the same direction. Let's try this once more. This is just one variation, same problem. Okay, so here we're given magnitudes and we're given the angle between the two vectors, and then we're asked to find the dot product of the two vectors. So remember, so our original formula here is the cosine of the angle between them, right, is the dot product divided by the product of the magnitudes. But if you multiply both sides by this denominator, this product of the magnitudes, you get that. And then I'm going to rewrite things a little bit, but you get that the dot product is the product of the magnitudes, if I can squeeze all this in here, times the cosine of theta. See, there's the equation we've been using. Just multiply both sides by the product of the magnitudes, and you get what the dot product is. Okay, so there's an alternative way of computing the dot product. Not that that's seems all that useful, right? Okay, but that might be useful to us at some point. Okay, so So we also know the dot product is these magnitudes times the cosine of the angle. Well, here we happen to know the magnitude. The magnitude of u there is 3, and the magnitude of b there is given to us as 7, right? And then the angle between the two vectors was pi over 3. So if we can just remember the cosine of pi over 3, then we know what the dot product is. What is the cosine of pi over 3? 1/2? Yeah. So we get for our dot product there, 21 halves. Yeah, pi over 3 is 60 degrees, right? Cosine of 60 degrees. 1/2. I think the remainder of these problems here is just some fun geometry. So these problems aren't all that consequential. It says plot this quadrilateral defined by these 4 points. So a quadrilateral is a geometric figure. It's a 4-sided geometric figure. So that's where the word quad comes from in the name. But the lateral means that the sides have to be all straight lines. Okay, so if you have, and the figure has to be closed. It's got to be a closed figure. All right, so if you have a closed figure, 4-sided figure, but all the sides are straight lines, that's a quadrilateral. So if you just plot 4 points in the plane, then you can connect those 4 points with straight lines, right, and get a quadrilateral. So here's the quadrilateral defined by those 4 points. Okay, it look like those. Now the book plotted, so it's plotted correctly. So notice that looks like it's a rectangle. It looks like it's a square, actually. Notice it's kind of a square, but it's a little bit tilted because this bottom part does not sit on the XY plane. This bottom edge of this point is slightly elevated above the XY. That's the 261. So it's slightly elevated above the XY. And you see, so it's looks, but look can be deceiving, right? Like you have square sitting slightly this point slightly on the XY plane. This point is exactly on the XY. Right? Notice Z, Z, Z. Okay. Well, the book draws a nice quadrilateral. It's going to be hard for us to draw. It's hard to solution of a point being above the XY plane. It's always that's always the tricky part in 3 space. Let's see. I guess what we want to know here about this quadrilateral is it a parallelogram? So, 4-sided figures can have all sorts of weird shapes, right? The sides do not have to be, in a quadrilateral in general, the sides do not have to be parallel to each other at all, right? So you can have, funky looking quadrilaterals. So see, that's an example of a quadrilateral because it's just a 4-sided figure where all the sides are straight lines, okay? But if you end up with some of the lines being parallel to each other, then you get, of course, more irregular, more symmetric figures. And these are figures that you're more familiar with, such as rectangles or squares or parallelograms. So a parallelogram is a quadrilateral where opposite sides are parallel, okay? So if you draw the quadrilateral so that opposite sides are parallel to one another, like in this picture, I'm trying to draw them so that the opposite sides are parallel, then that's called a parallelogram. But of course, so this is a parallelogram. This parallelogram is not a square or a rectangle. How do you get a parallelogram to be a rectangle? Yeah, that's right. The sides have to be perpendicular to one another, right? Okay, either parallel or perpendicular, correct? In a rectangle, and then of course you can refine that to a square. That's right. Okay, if you have a rectangle where all sides are equal, right? Okay, so so the more general figure is quadrilateral, right? And then you can refine that in various ways into other geometric figures. Let's see what we're asked here. Oh, so we want to show that this quadrilateral is indeed a parallelogram. All right, which means opposite sides are parallel. Okay, so you can check that easily without doing a bunch of slope calculations, okay, using vectors. All right, it's going to be hard to do slope calculations here because we're in three-dimensional space, okay, not in two-dimensional space, right? Okay, but you can do um, check here to see if sides are parallel by using vectors. So let's create some vectors here. Let's create the vectors that represent these two sides, right? Because these clearly in the picture, right? These have to be these have to be parallel sides, correct? Okay. So let's just write down what is that vector from A to D. And we'll just write it down there in component form, right? So the vector from A to D looks like, see, what's the first component? 0. And the second component is -2. And the third component is what? 6. And now let's find the vector from B to C. Okay. Now remember, this is not a force vector, right? So we don't care anything about the magnitude. We just want a vector that represents the geometry here in the picture, right? So from B to C, that looks like what? 0 and 6. Whoops. So those are definitely parallel, okay? Because in fact, those are the same vector, right? So of course they're parallel. These did not have to turn out to be the same vector, though. If they're going to be parallel, what relationship would we want them to have? A scalar multiple, that's right. So if one of the vectors, I'm so glad you said it beautifully too. If one of those vectors is a multiple of the other, right? A scalar vector, I'm sorry, a scalar multiple of the other, then they're parallel, okay? Well, they are scalar multiples of one another because this vector is 1 times this vector, right? Okay, and that is 1 is a scalar, correct? So indeed, those vectors are parallel. Now we have to check the other sides too, okay? Technically, but I don't think we could get these sides to be identical without having these sides parallel, right? But let's go ahead and check it anyway. So let's check the vector from D to C, and then also the one from A to B, right? Are they going to come out to be identical? So what is that vector from D to C? Is that -3, 4, and 1? And this one is that the same? -3 and 4 and 1. Yeah, right. So those vectors are also identical. So definitely a parallelogram. I guess the only other question we have to answer here is that these vectors are, since these vectors are all identical, I guess the only other question we want to know here is this a rectangle? So, because you see, you can have parallelograms that are not rectangles, right? So, want to test, is this a rectangle? So how can we see if that nice parallelogram is really a rectangle or not? I think good idea, Elijah, but I think you're thinking square, but rectangles do not have to be squares, right? Right? So you don't need the you don't need the lengths of the sides to have well, you do, but we don't need to immediately test the lengths of the sides. Is that what you were going to check to see if opposite sides had the same length? Yeah, okay. We could do that. All right. And that would work. But I was thinking of another way. Can you think of another? Just find the angles, right? Okay. So just to see if the angles turn out to be what, 90 degrees? Okay. And actually, we only need to test one of them, I think. Okay. Because if one of them is 90 degrees, then because it's a parallelogram, they're all going to be 90 degrees. Okay. So all we have to do is test one of these um, test one of these angles to see if it's 90 degrees. How do we do that? So for instance, this one, yeah, let me write it all down and then let's write it all down, but we can condense it really quickly. So we would have let's test this angle, right? So that would be the cosine of that angle. I'm calling that theta, right? So the cosine of that angle is the dot product, right? Of these two vectors. So that's A, B, that vector, dot A, D, this vector, correct, over what? Their magnitudes. But if this is a rectangle, what do we want this to come out to be? Zero, right? We want it to come out to be zero, right? Okay. And if it comes out to be zero, what's the only way this quotient is going to turn out to be zero? If the numerator is zero, right? Okay, because the magnitudes cannot be zero, right? Okay, they're positive. You can see in the picture the magnitudes are not zero, right? So the denominator is not going to be zero. It's just we're worried about the numerator being zero. That's just the dot product, right? So we just calculate to see if the dot product is zero, right? Okay, that's what we mentioned earlier. See, that's a fast test. See if two vectors are perpendicular. If their dot product is zero, does their dot product turn out to be zero here? Does it? Let's see. So 0 times that is 0, right? Is that right? And then no. So 0, what? And what? Positive 6, which is -2. Okay. Oh, phooey. All right. So we really don't care what the denominator turns out to be, right? Okay, because this dot product not going to be 0. Okay, so they're not perpendicular to one another. Okay, all right. So that's the check, right? Doesn't look like that nice parallelogram is really a rectangle. Okay. All right, let's have you guys. I'm going to have y'all draw one for me, but let's take a break here for a minute, okay? So we can gear up for this. So But here's going to be here's what's going to be on there. So on that set of axes you have, right, the bottom one, right, that you drew, that I had drawn, you just want to fill in the tick marks, okay, the x and the y axis and the p axis and the tick marks. So you've got a fourth quadrant perspective. So you're looking above the fourth quadrant, and then we're going to try to plot these vectors. That'll be fun because they're not going to come out great, okay? But we're going to try to plot those vectors and compute the angle between those two vectors. Let's see what between those two vectors is, right? Okay, so that's what we'll do when we'll come back. Let's come back in at 12, and then we'll try to do this. Okay, so all right. So everyone has their. I still have a couple of these left. On the second one, because probably you already drew on the first one. If I gave you a new one, you can still use the second. I'm going to go ahead and resume here and let y'all start, okay, officially, but you may have already started there, right? So again, you just want to try to plot those two vectors, but first, make sure you've got your axes marked properly, right? Your 3D set of axes marked properly. Try to do it from the fourth quadrant perspective, but if it doesn't turn out that way, that's okay. You can still plot these vectors, right? As long as you label the axes, okay, and label the tick marks, you can still plot these vectors. I think it maybe makes a nice picture from, well, sort of. At least it's a usable picture there from the fourth quadrant perspective, and then we're going to try to plot the angle between those two vectors. So you can do that just with the formula, right, without having to see the picture. But it's always kind of nice there to see the picture. All right, so you can have an idea if your numerical answer is correct. It's pretty clear, I think, once you draw these two vectors, if you get them drawn reasonably. It gives size. So that's nice. So hard to see vectors. Yes. You are. And so, check. Or we just give. Yeah. That's right. So, Since you've already completed it. So. You don't have to. Okay. So. Sounds good. So. Now let's. That gets this next slide. Now, two. This is the. That looks like that. But just. Well, so. The angle between them are. So that's how you do it. This. Yeah. Okay, so wait, you make this negative, this negative. I'm gonna see. So back to your third. So, but that's okay. You can do it. It's all right. You can still talk to that. Yeah. And even if you don't get the right fourth quadrant perspective, you can still plot the vector. Uh, keep in mind. Now, plus, like, bigger than 90.
I said. Actually. Bob. Oh, it's on the. Oh, I see. Yeah. Eagles. All right. Oh, that one's also. Get that one a moment ago. Oh, it's the same vectors. Same vector. Yeah, so you got to so I think vector. So that was negative. So so assuming that oh, all right. So oh, do we come out with the same vectors as before?
I didn't change my uh
Problems. As well, no matter what. So far. So, bottom. Right. Calculate. Okay. All right. So quickly here, y'all did a really good job. Even if you didn't get the right perspective on the axes, that's in terms of drawing the vectors, that's meaningless because you can put the vectors in no matter what perspective you got there on the axes. So to find the angle between them, right? It's just again, it's our formula. So it's u dot v there over those magnitudes. So I think that, and so that ends up being that theta. I think these end up being the same vectors we were using earlier. So it's something like 118.56. Is that what it was? 561. Okay. Degrees. Okay. Once you calculate the dot product in the magnitudes, and then take the inverse cosine there of that quotient, you get in degrees. Again, about 118.56, which I think matched everyone's picture really nicely. Okay, so y'all did a good job there of plotting the vectors. Now, just to preview coming attractions here for next time. Remember, in two-dimensional space, right? We talk about the direction of a vector, and that's the angle that the vector forms with the x-axis. But of course, things are much more complicated in 3 dimensions than 2 dimensions. So discussing the direction of a vector in 3 dimensions gets more complicated. So we're going to talk about we're gonna talk about that next time, but it's it's analogous to what we do in 2 dimensions. It's just a little bit worse. Okay. And then a topic though that we did not mention in 2 dimensions so far is topic of projection, what's called projection of a vector. And so I can't give a 25 word explanation of that. So we'll have to say that for next time. We'll provide the projection of a vector. Okay. But also something that will be useful to us in applications, and it's based on the dot product. All right. Okay. So that's what we're going to talk about next time. All right. So finish your homework, right? Don't delay finishing your homework for tonight. Y'all did very well on, I think this is the second one that's been due. Y'all did very well on the first one. So you want to keep that high average up, right? Okay. And we'll talk more again about the test next time. I think we have a better idea of where we're going to be.